Okay, so let's get started. Good afternoon, everyone. For those whom I have not met yet, I'm Bala Chandran, Chair of Mechanical Engineering. Together with Dean Sam Graham and Materials Engineering Department Chair JC Zhao, we want to welcome you for the very first talk of the George Dieter Distinguished Lecture Series, Mechanics and Materials. It's great to see everybody in person, as well as we have quite a number of people online today. In particular, a special thanks to UMD President Dan Moat for joining us in person, and also Carol Dieter, who's online with us today. Also, thanks to many of you who are donors in helping us make the series possible. Thank you again. So this lecture series honoring George Dieter has been an idea for us for some time. In fact, a couple of years ago, during his 90th birthday, the former UMD President Donald Pines talked about it, and then even during the last year or so, after George's passing in December 2020. When we think of George's time as a dean, many of us recall the innovations that he made in engineering education, because he was so passionate about students, he cared about students. But George was also fiercely devoted to research and design, mechanics, and materials as he was to students. He was inducted to NAE in 1993, and he developed a seminal book, Engineering Design, the 5th edition of which I hold out here today, in case anyone's interested. It's a foundation of our capstone design curriculum today. It also lives on the bookshelves of engineers around the world. When he passed, he was in the middle of the writing of the online portion of the 6th edition of the book. His co-author, the late Dr. Linda Smith, liked to tell how she was often asked, "You mean you're writing this with George Dieter, the Dieter?" She was asked to bring copies for alumni and friends on a trip to Abu Dhabi when she was visiting the Petroleum Institute, where she helped run a design course when she was there. The fact is, George's legacy will live on here at the Clark School for a very, very long time. We're pleased to present this lecture series to continue his commitment to innovative research and education. Our hope is that it will be a catalyst for faculty to make connections with leaders in the field for groundbreaking ideas, and that will shine a national spotlight on metal and engineering as a hub for inspiration, discovery, and advancements to change the world as we know it. This was always George's dream. And now I would like to welcome Dean Sam Graham to the podium to introduce our speaker. Dean Graham.
Thank you, Bala, and thank you everyone for coming to today's inaugural the George Dieter Distinguished Lecture Series. And we're happy to have a number of guests in the audience. I'd like to definitely point out Dan Moat and also online Carol Dieter, as well as our donors that made this event possible. George Dieter was a very important person here at the University of Maryland, and Dean Dieter paved the way for me to be here today. As I've heard that I'm the first dean from the outside of the University of Maryland since George, and he wrote a book, and so I guess I have to write one too. So we'll work on that a little bit later. But the thing is that his legacy continues today, and his impact on the engineering community still continues. I want to mention that during my doctoral studies, I worked with my advisor, who was David McDowell. And so David McDowell is also a person that is well known and highly decorated in the field of mechanics. Most people know me for my work in thermal sciences, a lot with electronics, but I've never totally left the roots of mechanics, which I started in, and most recently I was working on barrier films for flexible electronics. So you see flexible displays and things like that. Did a lot of work on the fracture of those coatings that we use for barrier film. So it still hasn't left me. I still dabble in mechanics every once in a while. So I'm quite pleased to introduce today's speaker, Dr. John Hutchinson, who is a giant in the field of mechanics and materials. We're indeed fortunate to have such a high caliber person as our inaugural speaker for the George Dieter Distinguished Lecture Series. Our speaker, John Hutchinson, comes from Harvard University. In many ways, he is considered the father of fracture mechanics. I know that many of you use these foundational principles and discoveries in your research today. He was inducted into the NAE in 1983 for fundamental contributions to the understanding of elastic and buckling of structures and the mechanical behavior and fracture of engineering materials. If you read papers by Dr. Hutchinson and Dr. Dieter, it's easy to see how their interests in mechanics and materials have helped to forge their respective careers. Dean Dieter was focused on the material processing and engineering design aspects. During Dr. Dieter's tenure as dean, we had our own illustrious figure in fracture mechanics here at the University of Maryland, the late Dr. George Irving, who was an active figure in the American Society of Testing and Materials and a member of the National Academy of Engineering. Dr. Hutchinson is a recipient of the Irwin Medal from ASTM, and in more recognitions, it includes the ASME NADI Medal. He is also a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and a foreign member of the Royal Society of London. Dr. Hutchinson will be speaking to us today about shell stability. We'll hear about the challenges in updating existing design codes for shell buckling and how Dr. Hutchinson is working to overcome them. Let's all please give him a warm round of welcome.
It should be good. Okay. Well, thank you. And I don't mean to correct the dean, but if I have to be called, I should be called maybe the son of fracture mechanics, because there is no question that George Irving was the father of fracture mechanics. Yeah. So, and I worked with George a lot. And as a matter of fact, I mentioned when we met with the dean today that I used to, when I was a young guy, go around the country with George to give short courses on fracture mechanics. So George not only fathered fracture mechanics, he also propagated it. He and Paul Parrish, yeah. Well, it's a great honor for me to be asked to come here today and address you. This is my first seminar in well over 2 years. I took this picture of George Dieter from the internet, and I think it shows many things, but I think it's very clear, makes very clear that deans can be human. And indeed, I've learned this morning in talking to people that George Dieter was much loved on the campus and has had lots of influence. More than 50 years ago, when I started out as a young guy, I worked on shell buckling. And of course, it was the space effort in those days that motivated shells. I mean, the 50s and 60s was the heyday of shell theory. And then roughly around 1969, 70, I pretty much dropped most of my work on shells and moved on to fracture, other things in materials. And, but about 7 or 8 years ago, there was a lot of loose ends in shells. By the way, when I've worked in lots of things, and I never drop any subject. And certainly I never dropped my interest in shells. And I just felt there were so many important things that weren't discovered and loose ends that weren't tied up back in the 60s that I started working on it again, just kind of on my own, on the side. And then fortuitously, I discovered, and first through, incidentally, the work of Pedro Reis, who was at that time had a group at MIT. He's up there. I learned that he was doing a wonderful set of experiments, which I'm going to talk about later in my talk. And it just so happened that what I was doing meshed perfectly with what I was doing, theoretical and numerical work, and it meshed perfectly with his experiments. And then things just snowballed. And another person up there, the only person up there who isn't a young person, is Mike Thompson, who's even older than me, believe it or not. And he had also worked in shells back in the 60s. And so Michael and I got back together and started doing some work. So these are some of the players whose names you'll see as we go through the talk. But I'm going to do something special. I put this together in a way that's, I hope, is accessible to a pretty wide engineering audience. And in particular, on the last 4 or 5 slides, I'm going to finish off by highlighting very recent work by young people in the field. So let's get going. Okay, and again, this for a structures person, I apologize because you'll know this, but this is, by the way, is there any way to make that black line disappear? You don't think so? Okay, okay. I certainly don't know how. So, yeah, so I want to just talk about the shell effect. And this example, or these 2 examples show that. So on the left is a square column constructed of thin plates. And this is, by the way, all my talk is going to be about elastic buckling. And on the right is a cylindrical shell with the same width, diameter of 2R, and the same thickness as that square column, cross-cut second column. And they're both subject to axial compression. And for the purposes of the discussion, imagine that they're both clamped at both ends. We're not talking about Euler buckling here. Be typical of a shell with an aspect length to width ratio that you see there in those examples. Now, if you look down below the square column, the analytic formula for a perfect square column, the stress at buckling is given by that formula, and it involves the radius to the thickness, but it involves only the bending stiffness. Buckling in plates, it involves bending, at least at the onset of buckling, only bending. So the D is the classic bending stiffness of a plate or shell of thickness T. Nu there is Poisson's ratio. Okay, on the right-hand side, the corresponding formula, essentially for the same sized column, but it's cylindrical, is that expression, and you'll notice, involves both the bending stiffness and the stretching stiffness. And the key point is that buckling in a shell, and this is the essence of the shell effect for buckling. Buckling can't take place without both bending and stretching. And as everybody knows, I will demonstrate this. Even I can do these kind of experiments. A thin plate or shell is very easy to bend, but amazingly stiff and stretching. So the shell effect is the fact that the buckling can't take place without both bending and stretching coupled together. And if you look at the bottom of the slide there on the left, you see the ratio of the plate column stress at buckling to that of the shell. And it's that simple formula. It involves only the thickness to radius ratio. And so for a ratio of 100th, and by the way, the 100th is a fairly thick shell. It's a ratio, it's about 6%. But if the more typical of a thin structure with a T over R of 1,000, the ratio is more like 0.5%. That is to say, the square column buckles at a stress or equivalently a load that's about 0.5% that of the circular column. That's the shell effect. It's huge. However, there's something else lurking behind the scenes. And if you look back up at the top, the post-buckling behavior of a plate-like structure, and that's plotted there as the average stress against the average end shortening. The post-buckling behavior is stable. In fact, structures, depending on the application, can be designed to buckle what plate structures can, and they can take more load. By contrast, look at the behavior of the cylindrical shell. As soon as it buckles, and by the way, those are plots, we're going to be talking about this, for perfect structures. As soon as buckling starts, there's a dramatic drop in the load carrying capacity. The buckling behavior is highly unstable, and depending on how it's loaded, I'm going to show you examples. The shell it may be able to snap to a stable state, but if it's got loads applied, it just collapses completely. So that's the shell effect as it applies to buckling. So we're stalled here. Let me try this. No, that's not. Oh, there we go. Okay. Yeah. Hopefully that'll work. Shall I try it? Let me go back. Oh, now it works. Okay. Yeah. Oh, okay. I can use the equipment. Great. Thank you. Yeah. So here's just two examples. On the left, that shell. So this is the top side of a glider when it's banking, and so the plates, they actually have slight curvature, but the plates are under compression, and you don't see them there, but there's stringers underneath the wing, and that's typical of a stable buckling pattern in a plate-like structure. And so, in fact, the old metal airplanes, I think maybe even back to DC-3s, they were designed to fly under certain conditions with buckled skins because it allowed for more load carrying capacity. For aerodynamic reasons, that's not allowed anymore. The structure on the right, I don't need to say anything about it, but that's a water tower that buckled and just immediately collapsed. You're going to see other examples of this. Okay, I couldn't resist including this very nice experimental paper by Mark Myers and some of his students at UCSD. And they tested, you can see, various eggs from a quail egg up to a goose egg. And the thing to notice is that for a typical chicken egg, in this test, so that you can see that these are loaded in axial compression, but they've been careful not to put concentrated loads, but to distribute the load. So that's actually an axial load. You can see that a typical chicken egg can take about 1,000 newtons, in other words, more than 200 pounds. And if you did, you can try this. If you take an egg in your hand, I suggest maybe you make sure you don't have a good suit on, and squeeze it. You can't, as long as you don't press too hard on one spot, you can't break the egg. And by the way, they repeated these tests for both eggs with the interior, and they evacuated them. And there's a little difference, but not much. Now, I should hasten to say, these eggs do not fail under this loading by buckling, but they're taking this load. They actually fail by a compressive failure mode. But again, that is the shell effect. If chickens laid square or cubic eggs, they wouldn't work so well. Okay, let's get down to work. And there's going to be a little history here. For those of you unaware of this, back in the 60s, when NASA was working flat out on shell structures, they collected data, and this is just for cylindrical shells under axial compression. By the way, this is all elastic buckling data. They collected data for design purposes. And the key, this data brings out the key thing about this unstable buckling behavior of shells. So let's start with that data plot. On the horizontal axis is the radius of the shell divided by the shell wall thickness. And so, as I say, thin shells often have R to T ratios of over 1,000. But that data goes down to R over T's of a bit less than 100. The material has to have a pretty high yield strain if it's going to buckle elastically at an R over T of 100, but these shells have. The vertical axis is the experimentally measured buckling load. Each one of those shells, data points, represents a different shell, by all kinds of researchers. But each data point represents a plot of the max load divided by the max load predicted for the perfect shell. I emphasize that. And the formula for the critical stress under axial compression is up there. Again, E is Young's modulus, nu is Poisson's ratio, and then the thickness to radius ratio. Okay, what you see is that there's huge scatter. Very few of the shells buckle even at half the prediction for the perfect shell. And in fact, there's lots of data down around about depending on the R over T, about 0.2. So, and just as an aside, let me tell you that in the 60s, when the shell community was confronting this data, and was all understood that this was real, there were quite a few people in the community that thought the problem was shell theory. The shell theory was giving the wrong prediction for the perfect buckling. It was not shell theory. It's the fact that the shell buckling behavior is so unstable, and coupled with that, and we'll talk about the details, is the fact that that leads to this extreme imperfection sensitivity. So NASA in the late 60s wrote a famous NASA special report, still used today, where they proposed as the design criterion that black curve. The idea being, and by the way, this is still in effect today. I'll have more to say about that. But the idea being that you take the prediction for the perfect shell, and then you multiply by this factor, which is roughly 0.2. And that is the expected buckling load. This is not a safety factor. This is the expected buckling. And as I said, and of course, this is specifically for these unstiffened shells. But this is the design criterion that still exists today. And you can see key players, there were many key players, but absolutely some of the most important players was W.T. Coiter, Warner Coiter in Holland, whose PhD thesis really was the classic on elastic stability theory and getting to the bottom of the essence of all of this. And even earlier, the work of von Karman and H.S. Hsien. H.S. Hsien, some of you will know who, it's a very weird story, but finally went back to China and headed their space. He was the nominal head of the Chinese space effort. Interesting books about him. So on the left here at the bottom, this is one of these cylindrical shells And I want to emphasize the way it's tested, you should think of it as being tested in a rigid test machine. So you don't apply the load, you apply the end shortening and measure the load. And so what happens when you reach the maximum load the shell can take, it snaps and buckles. But if you did that test under prescribed load, where you're piling on weights, it would do that. But because you're prescribing the end shortening, it snaps into this buckle condition. That very nice picture at the top showing that very regular buckle pattern. The only reason you're seeing that is because the experimentalists put a cylinder inside with a gap, a mandrel, to arrest the buckling deflection. So and locally it starts to buckle and then it can't go any further. So it buckles over the whole shell. Okay. We're doing good. All right, let me just point out, starting at the bottom there, this is data that's been put together recently. But this is the corresponding data, again, going back over a whole bunch of literature on the elastic buckling of spherical shells. And the data is rather similar. And as a matter of fact, again, NASA did this in the late 60s. The knockdown factor for designing spherical shells, unstiffened ones, is again about 0.2. There's some R over T dependence there. But the thing to take notice of here, and it's because some of these shells were manufactured so carefully, that a few of the shells, even way back, there was a group at Stanford that did electroplating of shells on very carefully machined wax subsurface. So they electroplated these shells, polished them, and then melted out the wax. They could make very accurate shells. And you can see some of them buckled up close to the classical value, but still enormous scatter. And as I say, still today, for unstiffened spherical shells or hemispherical shells, we still use that factor of 2, knockdown factor. Okay, now let me just show you. You're going to see this movie again because I want to use it. Oh yeah, thanks. I'm going to explain the details later. But this is a shell buckle. It's an elastomer shell. Nicely, I'm going to talk about that too. This is one of Pedro Reese's group's shell. And important to note, and I'll emphasize this in a moment, important to note that that is buckled under volume control. Not pressure control, but volume control. You think of it as water in there and the water is slowly evacuated. And the reason you see that dimple form and then get deeper and then go back is they're using a syringe. They first pump it out and then they pump it back. We'll talk more about that. Good. All right. Another point before we move on, and most of my talk is going to feature spherical shells, but not entirely. There's tremendous interest now, which was not the case in the 60s and 70s, in the life sciences and in soft materials area. And so, I mean, I'll just mention that the coronavirus is a spherical shell, radius on the order of tens of nanometers. But there's lots of interest in chromosome, colloidosomes. They come out to be nice spherical shells. They buckle. There's other examples. By the way, in the late 70s, I did consulting work for General Dynamics. And so this is a tank for one of these liquid natural gas tankers, which are very much in the news these days for obvious reasons. And you've probably seen these ships. They typically have 4 or 5 of these gigantic spherical tanks. They're made out of aluminum, and that's because for the material scientists in the crowd, that's because it's a cryogenic cargo. You don't want to use steel, probably. It's not obvious, but the reason I was a consultant is that the shell, thickness of the shell has to be designed so that it doesn't buckle. So the question is, what for this type of loading, what was the knockdown factor? That's the role I played in coming up with one. Okay, so here's the way my talk's going to play out from here on. I'm going to spend a little time talking about the way we analyze. I'm not going to do any details, but what has come out recently about very accurate analyses. Most of it's numerical analyses. I'm going to drive home this issue of buckling under, for spheres, prescribed volume change or prescribed pressure, because that's part of the picture. I'm going to talk about imperfections, imperfection sensitivity, and computing knockdown factors. Very recently, and here's where some of the younger people are going to be featured, I'm going to talk about energy barriers and probing methods for experimentally understanding elastic stability. And then finally, I'm going to talk about some things that really could also fall in the area of nonlinear dynamics. And I know that you guys have a number of nonlinear dynamic experts here. Okay, let me start with this. And again, I don't want to dwell on any of this at any length, but I'll just mention and give you an idea. So one of the things we could not do in the 60s, first of all, you remember finite element methods were in the beginnings, and certainly for nonlinear shell analysis, finite element methods were just starting to emerge. And even for nonlinear ODEs, the finite different methods that people were using could not do this kind of thing, at least not well. So what you see here is the result of this is a shell theory, but it uses exact bending and stretching measures. It is small strain, and the strains are small. So it's linear elasticity, the material part. The strains are small in these problems. It may not be obvious, but they are. And what makes this nice and easy is the fact that for spherical shells, most of the nonlinear behavior can be captured quite accurately, at least qualitatively in terms of the physical behavior, by looking at axisymmetric behavior. And so that means here, for these results, we don't need PDEs, we're dealing with ODEs. And, and everybody who works with numerical analysis these days knows they're very powerful algorithms for solving nonlinear ODEs, particularly for problems like these. I mean, these algorithms are so powerful. I use IMSL, but it's just one of them many softwares. So if you just look quickly, as I say, I'm not going to take long on this. This is a plot of the pressure always normalized by the pressure for the perfect shell, and this is for a perfect shell. The critical buckling pressure for the perfect shell. And on the other axis, the deflection at the pole. And so this is some full sphere symmetry about the equator. So this is the deflection at the upper pole divided by the radius of the shell. And so these problems are not hard to solve once you use the equations. And as I said, these are for exact stretching and strain formulation. And this just shows you how the deflection looks at different places on the post-buckling. Let me see if I can. Yeah, so this is the post-buckling pressure pole deflection curve. And the poles touch, that's the shape, at this point here. This is the corresponding plot of the pressure normalized by the buckling pressure of the perfect shell and the decrease in volume of the shell divided by the volume of a full sphere. And the poles come into contact at the point where the volume change is about 60, the volume loss is about 60% of the total volume. That's way beyond anything we're interested in. But one of the important things, but this demonstrates just how incredibly nonlinear the post-buckling behavior of these shells are. It also tells us, it's not obvious on this slide, but if you use the shell theory called moderate rotation shell theory, and this is a very usable nonlinear shell theory that was developed by Sanders and Coiter in the 60s. It is very accurate for pole deflections. This is what I find, less than about 20% of the radius for all values of R and T. Okay, let's do this. I'm going to show you this picture again. But before I do, let me tell you what we're seeing. As I said, this is prescribed volume. So, oh, there we go. This is prescribed volume. So what you and so the Reese group uses a syringe. By the way, these shells are only about this, and you can see this particular shell has a radius to thickness of 79. They're only about that size. And through the bottom, they remove water with a syringe. So they're controlling the volume. And so what we're going to see is we're going to go up to A. That's where it buckles. So this was a nearly perfect shell. Buckles at 80% of the classical. Because the volume is prescribed, it snaps the same volume down to B. And then, I mentioned this earlier, then they continue removing water and it goes out along this stable post-buckling curve, and that's down below 20% of the load carrying capacity of the perfect shell. And then, and they go way out here, by the way, and then they bring it back and it gets back to D, point D, and then it snaps back to the perfect state. So let's do that once more time, seeing that it. Yeah, and one thing that you may ask, how can it buckle under constant volume with a dimple? Because that's going to decrease the volume. The reason is that going along with this is that the pressure drops dramatically. You can see by a huge amount. And that means the shell, the elastic, which has deformed elastically, that means that all the other part of the shell can expand outward. So the dimple, the volume you lose from the dimple is replaced by the expansion of the shell that way. Okay. Now, let me show you what happens. And by the way, Joel Marthelo, he was in the group. He did this especially for this lecture for me at my request just a week ago. So this is under prescribed pressure, right? And what does it, think about it. Again, it's the same shell. We get up to A, it buckles. The pressure is held constant. Where can it go? Well, let's look. This is equivalent to when you stand on a beer can and it buckles. And as you know, when it buckles, it just flattens. These are elastic, so they spring back, and you can test them over and over, which they've done. Okay. Just let you read this. This is a beautiful test. That's just so you know, this is a tank car with about, it's more than a centimeter thick steel. And I'll tell you how it's loaded after you see it.
760. Gewonnen hat Herr Dr.
They blow it back up. They don't. Okay. What they've done there, and that was done deliberately, but this is real. This is under prescribed pressure. And what they've done is they filled the tank car with water. They sealed all the valves. Normally, when you evacuate a tank, you have to open a valve at the top or you're asking for trouble. They don't do that. And I don't know if you noticed, but there's a hose at the bottom. So the water is drained out from the bottom. And I'll just state as a fact, even though this is a half-inch or almost half-inch thick steel shell, it buckles at about 1/2 an atmospheric pressure. So by the time the water in that tank is about half down, boom, catastrophic. And I'll just remark that the cylindrical shell under hydrostatic pressure, so that's what this is not as catastrophic as the cylindrical shell under axial compression. Okay, you know what? I'm not gonna spend time on this, but Stu Antman's here, so I'll let him just look at that for a second. So the thing, again, that was not possible in the 60s, I want to make the point. Poiter, he was my hero in mechanics, Dutchman. He wrote basically his last paper, the last important paper, and it was a 100-page paper on the buckling of spherical shells. And it's a real tour de force, but there were so many things that he could not do because he was working only analytically. But with numerical methods, with great accuracy, you can ask all kinds of questions and get all kinds of results. And I'm not going to dwell on it, but one of the interesting things is that this shows that as soon as, and this is what the analysis, and as I say, a graduate student who's good at numerical analysis, once he gets the equations right, can do these calculations. But what this shows is that as soon as the shell starts to buckle, this is the classical here at the bottom here. This is the classical mode, and this was derived by a Swiss, I think, named Zoli in 1915. As soon as it starts to buckle, that shape gets lost and it goes to it's a localization problem. The buckling localizes to the pole. Immediately. So it's amazing how abrupt that process is. I'll say no more. But I will say a little bit about the results of our analysis when we include imperfections. So, and this was done once I teamed up with Pedro Reis and his group. This was done, as you'll see in a second, to make connection with their experiments. So this is quite a realistic imperfection. It's axisymmetric, it's located at the pole, and as you can see, it's a Gaussian-shaped dimple. And delta is the imperfection. So I should say something. And there's a lot of history of this. But the worst imperfections for these types of these unstiffened shells is slight undulations of the geometry, of the middle surface geometry. And the amplitude of this imperfection is delta. And you'll see here that here's calculations for, first of all, the perfect shell, but for 3 other imperfections. The largest one, which is just 1 thickness out of roundness at the top. So, you know, for a thin shell, you probably wouldn't even recognize by eye a 1 thickness imperfection. You certainly wouldn't recognize one that's a 1/10 or a 1/4. But notice that here's the quarter right here. Notice the quarter of a imperfection of a thickness imperfection reduces the buckling load to almost 50%. And when they're down on the order of 1 thickness, they're down to that 0.2 ratio. Here's the same results, but here plotted as the buckling pressure, and this is the maximum pressure that this shell in the presence of the imperfection can carry. This is the imperfection amplitude divided by the shell thickness. And I didn't mention, and it's not obvious why this is, but these results normalized this way are independent of the shell thickness. And so lo and behold, you see that what emerges here is this plateau at just about 20% of the classical pressure. And even for quite big imperfections, it doesn't get below that. Now, the Reese group, and I'm doing them no justice because they really developed this absolutely terrific way of manufacturing very precise elastomer shells. And they build in precise imperfections of these shapes. And here's their experimental data, different R/T values. Here's their experimental data plotted against the built-in imperfection amplitude. And I have to say that this is unquestionably, in my mind, certainly for spherical shells, but I think for any shell, the most systematic imperfection sensitivity data that people have, anybody's generated. So this is, you know, this is one of these new developments. Okay, now I'm a structures guy. That ought to be clear. And certainly when we were all working on shells back in the 60s, we were mainly concerned with the maximum load carrying capacity, the buckling load. And for structures people, that's, I'm going to say some other things about other interests in buckling in a moment. But for structures people, that is still the main motivation. And there's a big effort underway. It's been going underway for more than 5 years at NASA. It's led by Mark Hilleberger. And by the way, similar activities are going on in the European Space Agency and in the Chinese Space Agency. In fact, I would say there's more activity, certainly on the theoretical side in Europe than there is in the US. But here's what NASA is doing. And let me start off by saying the codes that we have, you know, Abacus, ANSYS, the structural codes, if you put in the right imperfections, an accurate representation of the imperfection, and other things like, you know, these shells are often segmented, so you need to put in how they're joined and that kind of thing. That can also lead to perfection. But if you put that in the codes, those codes will unquestionably give you results to better than 5%. You know, and so for engineering design purposes, those codes are great. But see why? You have to accurately represent the imperfections. So what NASA has been doing, they had about 5 or 6 big shells left over from the shuttle program, and they used those. And by the way, some of these shells are stiffened shells. They measure the imperfections. They turn the codes on to, with those imperfections, compute the buckling load, and then they do the experiment. They test the shell. If you go online to YouTube and look under Hilleberger, you'll see some full-scale tests of these gigantic shells. They're kind of interesting to see. And you know, and other things are going on too. So, but you know, obviously one difficulty is with such an approach to rely on computation, which is what, yeah, so I should say that in the shell community, there's a general feeling by almost all people, designers and modelers, that the codes are too conservative. And you can see they're empirical. They take the line, they took in the 60s, they took the line under the lowest data, and then they said, that's where it's going to buckle. But the problem is, if you're going to feed in imperfections, you have to know what the imperfections are. And if it's a thing like a big shell, what are the how do you know what the imperfections are going to be before it's built? Well, maybe you specify tolerances. So there's lots of things here. But anyway, my own feeling is that, and you probably just saw from the data I showed you, that for unstiffened shells at least, you've got to design for thin shells, for those two classes of shells, you've got to design to 0.2, unless you know the imperfections are smaller. At the same time, I think there's lots of scope for stiffened and composite shells. And by the way, in space applications now, they're using more and more composite shells and stiffened shells. Okay, so how are we doing? Okay, I'm getting there. There are two new things coming up. There's, for a shell that's loaded up to a point below its buckling load, there's an inherent energy barrier, which we can compute, between the shell at that load and for it to buckle. And one of the ways to assess that is to use probing. And so here's a very nice, extensive series of tests using thousands of Coke cans has been done. These were colleagues of mine at Harvard. And here's just one example. And I want to go through this plot. So here is a Coke can. And by the way, Coke cans, they buckle elastically. Of course, once they snap, they go plastic. But before they snap, they're elastic. And a typical Coke can, when you test it, buckles at about 30% of the classical for a perfect shell. So typical shell for their radius to thickness. So look at this. Here's a load applied to the can. And by the way, this is prescribed end shortening, not prescribed load, but that's the load associated with that end shortening of 136 Newton. And it's probed laterally. And look at the probe forces we're talking about are only measured in newtons. But when the load is very low, you can probe it and it doesn't buckle. But let's look at the other extreme. Here's the same can loaded to over 1,000 newtons. So that's a Coke can carries over 200 pounds before it buckles. So you can stand on one. Some people can. And it's probed, and you can see when you probe it, this is, Okay, this is the probing curve. So the probe force increases, then it starts to give a bit. You're still probing. You got to stop at A, otherwise it'll snap. But at A, it'll snap. And so this can, and you can cross plot these and extrapolate to the point where it'll buckle. And it buckles at, I think, at about 1,100 newtons. Here's an example of this. The probe, by the way, is coming from behind. So this is a dynamic picture. This is taking place in just milliseconds. And so what's happened there is it's probed from behind. It starts to buckle locally. These short wavelength modes dynamically sweep around the can. Notice that again, this is not prescribed load. As I say, if it had been, it would do that. But this is prescribed and shortened. And so it is a localized mode. I'll play it once more, but you can see in the very beginning, you see these short wavelength modes, and then they expand to the longer wavelength modes. So it's a very dynamic process. And that's not easy to analyze dynamically, although you can. Some people can. Okay, here's I'll make this quick. This is very nice experimental work by Joel Marthelo. Let's just start. This is this hemispherical shell under prescribed pressure, but below this is schematic, but below the buckling pressure. And I'll let you think about it, but the energy barrier under this type of loading is the work done by the pressure through the change in volume. And so that's the energy barrier to buckling. The difference between the energy in the unbuckled state and the buckled state, it's an unstable buckled state, at the same pressure is that's just schematic, but is that amount. So this can be computed accurately, particularly for these axisymmetric deformations. And so we've done that, and Joel did the experiments where, there's no movie here, but where he, once it's loaded in pressure, and this was prescribed pressure, he then probes it until it fails, and he measures the work he has to do to get it to buckle. That's actually an upper bound to the energy barrier, but it turns out for this configuration, that is essentially the energy barrier. And just remarkably good agreement between theory and experiment. There's a young guy, graduated from Caltech, working with Sergio Pellegrino and JP. This is JPL work too. This is Fabian, by the way, is soon going to be starting as an assistant professor in aero at Cornell. And their group designs these collapsible structures meant to go in space. And so this picture, this slide isn't so great, but this is the structure in question. It's a model of the structure in question. Everything else is a test separation. But this group, and by the way, they're getting a full-scale version to go into space in just a couple of months. But this is for solar cells. So the full scale, this is just a model, but the full scale version is about 18 feet long, probably about a meter wide, and it's solar cells, thin film solar cells. And the spars on either side are coilable, sort of like a measuring tape, are coilable. So this is rolled up, this whole structure, this monster structure is rolled up. It's in a thin tube, and in space, I don't know exactly how they do it, but it's released and it just unfolds all by itself, just releasing the stored elastic energy. Now, in space, if you think about it, the only pressure loading is photon pressure. So these things, they worry about designing them against photon pressure and buckling. So that's what all these experiments are innate of. And so in particular, this is the model structure. I think it's about 3 feet long. And you can't see them, but there's no film, but there's connecting battens or rods between those two members. And I'm going to play a movie. You'll see. And basically what they're doing is probing, in this case, at the center to see the nature of the buckling. So I'll give you some running commentary as we. So on the right, there's the deflection of the probe. I didn't show you this, but you see a snap. And now it's picking up load again. Anyway, so what is it that I apologize. For example, what happened there is you first see snapping under the load. And then as the punch engages again, you see more snapping, but that's occurring to the side, and you didn't see that. But anyway, but they use this probe, and they probe it all over. They use this probing method to get a feel for the energy landscape of this type of structure. Okay, now here's some local people. Together, one of my young colleagues, I consider all these people very young. Tatcha Bertoldi is my colleague at Harvard. And they're doing, and this is just representative, but there's a lot of work like this going on recently. And as I say, in one sense, you can think of it as being in part of the general dynamics framework. And this is a series of arches. They're all connected. These are free rotating joints where they're connected across. And this is a probe. So it's being probed here. The bottom two pictures are the models. And this is the top picture is the experiment. And by the way, it's the top picture, and they're all running together, but the top picture is slowed down to because it's snapping, and they want to capture as much of it as possible. So you see, it'll suddenly snap to another stable state. There it goes. And they've done, again, they probed in different directions. They have much longer examples of this where they can probe here, make things happen here, vice versa. So this is just illustrative of quite a bit that's going on. And in some cases, it has to do with using this unstable material structures behavior to design materials. And Pedro Ruiz coined the phrase buckophilia as opposed to buccophobia. So when I and any of the older people in the crowd worked on buckling in the old days, we really were working to avoid buckling. But a lot of the applications today, in particular, to get these metamaterials with these unusual nonlinear properties, they want buckling, and they want to design and be able to control it. That's what Pedro means by buckophilia. Okay, my last slide. I'm running a tiny bit over. Sorry. But yeah, so I'm going to first start with something that I saw for the first time in my life 2 weeks ago, and it was Renee Zal who demonstrated this to me and who gave me this ring. And, you know, I was mentioning to Stu Antman, by the way, Stu Antman made basic contributions many years ago to what's called Kirchhoff rod theory, and that's what governs a structure like this. Kirchhoff, incidentally, did his work 1850, somewhere, 1859, maybe. Okay. Anyway, it doesn't bother me. I even love Euler's work. Anyway, I'm just showing you this effect. So I'm simply twisting this in opposite directions, and lo and behold, it snaps. I was still holding, but so you didn't see the snap, but it snaps into 3 rings. Now, why 3 rings? I wish I had a very good mathematical sense of that. I don't. So I've been thinking about this ever since Renee showed me this. So, and this is stable. And by the way, one of the things I haven't told you is if you did this with a ring with a circular cross section, you would not get this stable 3-ring configuration. But this ring has a flat ring with about a 4-to-1 aspect ratio of the cross section. And by the way, this is all elastic, all elastic. It's a high strength steel ring. Okay, now I want to do it without hurting it. Yeah, so I'm not good at undoing this because I think I'm actually doing it in the wrong way I should. Let me try something else. God, I'm ruining my demonstration. All right. Here, let me go again. I did this twice already today. I think I'm pulling it at the wrong place. No, I'm sorry. I'm goofing this up. Anyway, if I pulled it the right way, it would just snap back to the nice circular ring. I don't know why I'm not able to do that, but oh, there we go. Yeah, so yeah, as you see, I'm not an experimentalist. Okay, but let me just say a little bit more about the work that Renee Zal and her group are doing. So Renee is a recent assistant professor at Stanford. She's been focusing on hexagonal shaped rings. They have the benefit, as you see pictured here, that they can be used to tessellate a 2D surface or make 3D structures. And so I don't have a movie here to show you this, but this just illustrates that this structure has units like this can be folded into something that looks like this. And similarly, these type structures can be folded into something like this. And it's folded into a stable configuration. And then given that you properly deactivate it, it snaps into a structure. So these are structures, or if you want, materials designed to snap from one state or another. And so obviously for certain applications, this is very useful stuff. Okay, I'm sorry, I went over by a few minutes, but quickly, yes, for shell structures, we are going to have to figure out a way to deal with imperfections. And if we want to take advantage of the computer codes, we're going to have to put in realistic imperfections, either measured or using the imperfection level to set tolerance for manufacturing for shell structures. As I indicated, this notion of the energy barrier is relatively recent. It actually goes back a long way, but to actually compute it is recent, but its implications aren't well understood. And certainly probing, which is a new idea, has lots of potential, but it needs a lot more work. And then, as I've indicated, there's so much going on, both in soft materials area, the life sciences, and in nonlinear material behavior to exploit the nonlinear instability behavior of materials as a bucklephilia phenomena. Thank you. Thank you. Yes. Correct.
Well, the circular one.
Correct.
Now, if you have a cross section.
There is. And yeah, if you, the thing, and actually I've worked on that, and there's some nice experiments on that. If you have an elliptical cross section, the curvature is highest here, so it doesn't want to buckle there. So if you did a test or do the theory, it wants to buckle first, the reason of lowest curvature. Yeah, and exactly how it maps on to the rectangular cross section, I'm not sure, but the effect is very clear. Yeah, and as a matter of fact, the experiments show this too. This is why I got interested in it. If the ellipticity is sufficient, then the buckling, the initial buckling on these sides may be unstable, you know, the little snap, but this part doesn't buckle. So in that sense, the shell is still stable. It's still carrying most of the load. Yeah.
Thank you. It was very fascinating. And
Thanks.
it's a great honor, I think, to
Well,
George.
it's a great honor for me. And I especially after being here this morning and hearing how much everybody thinks of George Dieter. Yeah.
Yeah, he was one of my first experiences here as an assistant professor. Is he was a guest judge in my engineering design course, and it was, I mean, he was just, I didn't even know really who he was. He was just a judge that showed up, but he was so collegial. It was really great. So this idea that if you understand the imperfections, you can predict the buckling. You seem to be presenting that in the context of static imperfections.
Yes.
Can you comment on dynamic imperfections, such as might be originating from turbulence or something like that?
Or if you come along and bang the shell. Yeah. Well, you know, in a way, that's what the energy barrier, how that could be used. And we've done some work on that. I did work with Thompson and Schieber. They were two of the guys on the first slide on exactly that problem. But I have to say the dynamic buckling problem is not nearly as good. It's not as well understood as the static. Yeah. Yeah, no, Coiter's great contribution was, I mean, it still is, he tied together the analysis of the perfect structure with the imperfection sensitivity. In other words, basically, his analysis method uses the analysis of the perfect structure, but then the imperfection feeds into that, And so the two, you get both in one package. Yeah. And so that theory is of great generality. Yeah.
Thank you.
But his analysis is all static. Yeah.
Other questions?
Budiansky and I did work on dynamic buckling again in the 60s. Yeah.
Other questions or comments? Okay, Stu.
About 20 odd years ago, there was a mathematical theory called singularity theory. And that was a theory of imperfections in which the statement was you need a fixed number of imperfections to characterize qualitatively any sort of bifurcation that will take place. Has this been
Is this
used?
catastrophe theory? Are you talking about catastrophe theory?
No, no.
Oh, okay. No.
It was called singularity theory.
Okay.
And so has that had any effect on these studies or?
Well, I probably revealed the answer to the question. I was unaware of it. But certainly it is true that I don't know how singularity theory that you're referring to relates to catastrophe theory, but certainly it is true that each of these buckling type behaviors has a characteristic, I'll call it a singularity. And you can tease out different kinds of behaviors by putting in different imperfections. And then you get one behavior or a different response. But I have never thought about it in the one-to-one terms you mentioned. And I was unaware of that theory. Yeah.
There's a book by Golubsky and Schaefer on.
Okay, yeah. No.
Notice.
Take advantage of every possibility.
Yeah, well, that's interesting. That's interesting. The thing is with these cylindrical and spherical shells, and as you can see, the buckling is local. So, you know, I'm not saying it would be different type buckling, but having an imperfection here, you got to have it here. If you had the same imperfection over here, you basically get the same result. I don't know if that's considered a different imperfection or the same. Yeah, you got lots of symmetries. That's right. That's right. Yeah.
I come from a different background, and I enjoyed your talk very much. I feel like I learned a lot. I didn't know anything about all this shell behavior, but coming from a material science background, I was just thinking, especially like with the experiment of the Coke can and things like that, whether other defects, like I'm used to thinking of defects like dislocation, grain size, grain boundaries, and things like that, how would they affect the behavior of the buckling of these structures? Do they enter at all or not?
You know, I didn't get the thrust of your question.
Oh, sorry.
So
how would other defects such as dislocations, grain size,
okay.
grain boundaries, and things like that would enter into this? Do they affect it or not?
I can tell you, here's one example. As you probably know, if you have perfect single crystals and you load them in different ways, for example, you could load in hydrostatic pressures, and certain crystals, due to the nonlinear elastic behavior, certain single crystals undergo phase transformations. Now, those types of phase transformations, basically flipping from one crystal structure, lattice structure, to another. Mm-hmm. Those kinds of things are governed by these kinds of, mathematically we call them bifurcations, if it's perfect system, these kind of bifurcations. So, and that kind of, some of that has been applied. Rodney Hill and I've forgotten who else it was, did some of that work related to these kind of single crystal transformations. Now, I don't,
But for example, in the case of the Coke can, that's not a single crystal.
I don't think so, no. No,
We have done TEM on Coke cans.
I see, okay, yeah.
Thank you.
Thanks.
As a small token of appreciation.
Thank you. Good. Thanks. I really appreciated being invited. Yeah,
Jason, you wanna come?
yeah.